Up the recording
Okay.
during the Q&A.
Okay. Also, there are drinks in the back. The food is on the way, but it's coming. um, okay. So this thesis focuses on trajectory modeling, which can be defined as the process of predicting or generating sequences of states and actions that represent the behavior of an agent over time. Trajectory modeling has a variety of important use cases in robotics. So for example, in RoboCup, we may need to predict the trajectories of our opponents to make decisions. Similarly, in autonomous vehicles, let me move this. Similarly, in autonomous surveillance applications, we may have a similar type of problem where we're monitoring enemy assets, but the domain is much sparser and has more uncertainty. On the flip side, robots may need to plan their own trajectories, such as in robot manipulation, where we may have to produce a series of joint angles or actions to complete a task. And in the self-driving vehicle domain, we see both aspects of trajectory modeling, where we want to jointly predict the trajectories of the other vehicles on the road and also safely plan our own route. These types of trajectory modeling problems have typically used a wide variety of classical methods. So for example, if we're trying to find a path for a drone that doesn't collide with any of these walls, we may use trajectory optimization. On the other hand, if we're trying to estimate the state of a robot or the state of another vehicle, we may use methods like Kalman filtering or particle filters. And finally, if we're doing motion or path planning, we may use sample-based methods like RRT-SAR or graph-based methods like A-star. While these traditional approaches are high-performing, but they require expertly crafted heuristics and motion models that may be hard to specify. So to address the shortcomings of these traditional approaches, we propose a unifying, data-driven generative modeling approach where rather than using expert knowledge to learn how to accomplish tasks, we rely on data collected from the environment. However, there are still several open questions about these approaches, such as how to best model constraints, how to deal with multi-agent trajectory forecasting and planning, and can end users utilize these models efficiently. So this thesis focuses on a variety of domains through the lens of generative modeling, and the core areas being target tracking, trajectory forecasting, multi-agent coordination, and scheduling and motion planning. Recent work in generative modeling has revolutionized how we can efficiently learn multimodal data distributions. This has led to large advancements in models like text-to-image and large language models. Recently, researchers have been using these generative models in several robotics applications, like imitation learning. In our work, we specifically build upon recent works in diffusion models, flow matching models, and large language models for a variety of domains. A large part of this thesis is focused on this target tracking and trajectory forecasting domain, where the objective of target tracking is to estimate the state or trajectories of a moving object. Traditional methods work best when there's a known motion model of the target and when there are sufficient observations of the target that we can use to update our state of the world. In this work, we instead do not assume any motion model of the target. Recent work in trajectory forecasting has many similarities to our work, where we take inspiration from self-driving vehicles and social navigation problems, where in these domains, the goal is to estimate the trajectories of other vehicles and pedestrians. However, unlike these domains, the target we are trying to estimate in a lot of our work is adversarial. And this makes learning policies and state estimators much more difficult. Finally, we build models for multi-agent coordination, scheduling, and motion planning, where recent work in deep multi-agent reinforcement learning has revolutionized how agents can autonomously learn how to coordinate and achieve human-level performance in a variety of games. In the top left, I showed StarCraft, which many see as one of the most difficult environments that we've achieved success in with reinforcement learning. However, StarCraft is actually in some ways easier than some of the domains that we explore because information is dense and there are always clear objectives that you can do to maximize reward. So in summary, this thesis explores multiple areas of predictive generation and forecasting using generative models. And there's three main parts of this thesis. And so the three hypotheses are: one, that generative diffusion models with additional constraint satisfaction can improve accuracy, where accuracy will depend on the domain. Two, leveraging generative models for multi-agent reinforcement learning can increase agent performance. And three, generative LLMs can lower users' workload, increase usability, and produce better plans in a scheduling and motion planning task. So in the first part of my thesis, I developed models for predicting the current and future locations of an adversarial agent. And I'm going to introduce this prisoner escape domain, which a large amount of these works in my thesis use. So in the prisoner escape domain, we take inspiration from many real-world surveillance applications, and we specifically model a scenario where a fugitive has escaped and is heading towards one of several hideouts. The goal consists of a team of heterogeneous blue agents who are trying to capture or track an opponent agent. And the goal is for the red agent, meanwhile, to discreetly go to a target destination. Additionally, there are environmental constraints in prisoner escape where visibility is reduced on the darker regions of the map. And when agents are in close proximity with one another, they have the ability to detect each other and obtain information about the positions of the opposing agents. So there are three key challenges we tackle in these types of domains. First, we define sparsity as infrequent information about the opponents. Second, we define partially observable, that at each time step, agents have incomplete information of the full world and opponent states, and the environment plays a factor in this as the domains have a large state space, and the vision of the agent is comparatively small. Finally, we study an adversarial game such that the opponent can be intelligent or have various strategies to impede our own capabilities. And in this first work, we're going to be looking at filtering and prediction, where given some past detections about the adversary, we want to know where is he now and where he will be in the future. So we begin by collecting a data set consisting of interactions between the two team policies. We use an invasive A-star planner for the opponent decision model, and a heuristic search and tracking policy for the blue team. SB, or the blue states, refer to their blue agent positions throughout the world, while the observations refer to the detections of the adversary. And we feed this into our prediction model to estimate the current and future states of the opponent. We collect the data set offline and use a supervised training scheme to train the model. Having a multimodal hypothesis is crucial in our domain, as prisoners could be at many different locations. So in this example, if we have observed the prisoner multiple time steps in the past, and then it moves into, we haven't observed it for a while, it could have gone to many different locations. So we represent our hypothesis as a mixture of Gaussians, and here is just a visualization of a mixture of three Gaussians, where each point will represent where the prisoner is. So in this first work, our architecture starts with a LSTM block to encode the history of detections as an approximate belief state. And we choose an LSTM because it's designed for sequential data and can handle a variable number of past detections. Then we use the decoder to fit our mixture of Gaussians through maximum likelihood. However, we found that some of the components of the mixture may disappear or overlap. So to maintain distinct multiple hypotheses, we add a mutual information regularization term where we maximize the mutual information between each Gaussian component. Each Gaussian component in the embedding E. So this term essentially regulates each component of the mixture to be as distinct as possible. And finally, the agent position encoder encodes the history of the blue states, and we get this embedding through both an LSTM and GNN layers. So sometimes we ablate this part of the model, as we may not always know how we got the detections of the adversary. And for example, if they're passed with by foreign intelligence, they might not want us to know where the locations of their assets are. So here's a visualization of the results. So we can see that there's a mountain here, and the prisoner may have to go to the above the mountain or below the mountain, and we have like these distinct Gaussian hypotheses to go around the mountain. In terms of log likelihood, our models here on the far right outperform the 3 learning-based baselines, and we find that it increases performance across all 3 time horizons, where 0 minutes is the current state, and the 30 minutes and 60 minutes are predicting into the future. So while Gaussian mixture models are great, they're limited to the parametrization of the mixture of Gaussians. Predictions do not have consistency across time steps, and we're also limited to predicting a single adversary. So this next body of work will look at diffusion models, which are non-parametric formulations or predictions. They produce full trajectories extending to arbitrary number of time steps, and they predict the trajectories of multiple adversaries. So in this domain, again, we're moving from single agent target tracking to multi-agent target tracking. And this provides another challenge because in many real-world cases, we cannot assume the identity of a detection. So for example, if the X's denote where the previous detections of the adversary are, there could be many hypothetical tracks. And on this first example, the red and purple adversary could have crossed paths, while in the second example, they travel in parallel. So adversaries might cross paths intentionally to obscure the primary target, thereby creating uncertainty about which target went in which direction. In addition to these 2 hypotheses, there could have been many combinations of assigning the detections to the identities of the adversaries, and this poses a challenge as we want to generate hypotheses without having to know which detection belonged to which agent. So to tackle this problem, we use generative diffusion models, and diffusion models have recently gained traction in text-to-image generation, where they can adeptly learn multimodal data distributions. On the right, we show the generative process of our diffusion model producing 3 agent trajectories. And to produce these trajectories, we directly diffuse them, denoted as tau, and tau represents a sequence of opponent states. And the diffusion procedure consists of 2 processes, a forward process, which adds Gaussian noise, and a backwards process, which iteratively removes noise. T denotes the total number of diffusion time steps, where tau T converges to complete Gaussian noise. I then denotes the diffusion time step, and tau 0 denotes the trajectory drawn from our linear distribution. So the core idea of diffusion models is to match the forward and backward processes so that we can learn a neural network to iteratively denoise to produce trajectories that lie within our data distribution. So I'll briefly describe how diffusion models are trained. The neural network, denoted as epsilon theta, needs to learn how much noise to remove from a noisy trajectory at each diffusion time step I. For the training procedure, we do gradient descent on this loss function, where first we sample a ground truth trajectory tau 0. Then we add varying amount of noise based on the drawn diffusion time step I to get tau I. And finally, we compute the MSE between the noise that we sampled and the predicted noise from our neural network. This MSE loss has been shown in prior literature to drive the neural network to invert the forward process of adding noise and learn the backward de-emission process. So now I show our model named Cadence, where first I'm going to show diffusing for the trajectory of a single adversary. So we feed the model a noisy trajectory, and we want to denoise this down. And our model is still conditioned on the detection history, which is still passed through an LCM. And this detection history through the LCM is the same as our previous model block. Unlike our previous work, we do not condition on blue tracks in this work. And this process is repeated t times to go from complete Gaussian noise to a trajectory that lies within our data distribution. Next, we use the same ways to predict the path for another adversary, where we condition the generation process with the same detection history information. Then we use cross-attention here in the center to communicate information between the two tracks during the generative process, ensuring that the tracks produce unique hypotheses for each adversary. And the cross-attention mechanism is crucial for the model to be invariant to the number of adversaries that we need to track. So a final contribution of our work is constraint guided sampling, which ensures that the generated trajectory complies with the known constraints. So on the left, we see that there are several mountains denoted as these plus signs. And if we know where these obstacles are, we can formulate this as a constraint optimization problem where the points in the trajectory should not overlap with these mountain points. So if f of mu is the objective that the diffusion process is minimizing, we can reformulate our constraint as an inequality constraint with a Lagrange multiplier to turn this kind of into a cost function. So now we just define j of mu, which is our cost function, and we can use this cost function to guide our diffusion sampling process. So for clarity, the neural network model learns the noise of each trajectory sample, but we can convert this to the predicted mean μi of each state in the trajectory. And with this formulation, we can then push the state of our trajectory away from the obstacles during the diffusion sampling process, as shown by the picture here. So for our multi-agent results, we ablate the assumption that we have the identity of detection. And first, we assume we do not have the detection identity and use a single LSTM for all detections. Second, we assume the detection identity is known, and we can assign each detection to the corresponding adversary. So in our work, we predict the paths of 3 adversarial agents. So on the plot on the right, on the y-axis, we show the distance error between our generated path and the ground truth paths, and the x-axis denotes the prediction horizon. And solid lines indicate the average error across all generated samples, while dotted lines indicate the best estimate to the ground truth trajectory. In our domain, knowing the detection origin helps predictions in the short horizon, and the differences become smaller in the long horizon as the adversaries move towards a fixed set of hideouts. Additionally, we show that our models can generate trajectories that are close to the ground truth track, as indicated by the difference between the solid and the dotted lines. We also benchmark our model, a single target tracking version of our model against prior approaches on my previous work, and our results show that our model matches or exceeds the established benchmarks at the prediction horizons. Furthermore, our method's ability to generate complete trajectories allows for training a single diffusion model to predict across all 120 time steps, unlike the previous method that required training separate models for each time horizon. So the main takeaways from this work are that Cadence can produce multimodal predictions for multi and single agent adversarial tracking, improving tracking by 9.2% and reducing obstacle collisions by up to 90%. So moving from just the adversarial tracking domain, my next body of work extends the generative modeling framework to a variety of different domains. One being this aircraft trajectory forecasting, and also long horizon path planning, and also for imitation learning for a table tennis robot. So similar to the adversarial tracking domain, in all these cases, we're given a data set of trajectories representing either a sequence of states or a sequence of state and actions. And in the adversarial tracking domain, we were specifically looking at it because it was sparse and partially observable. In the trajectory forecasting, where we're trying to forecast the future trajectories of the Cessna aircraft, we also want to see if these models help due to the multimodal behavior of this aircraft. And long horizon planning we want to look at because it's has been traditionally hard for reinforcement learning methods to do this kind of task. So additionally, a main motivation in these domains is that we want to reduce the sampling time of the diffusion models, as agents or robots may need to act quickly and make decisions quickly. And the main thing I'm just denoting here is that the left two domains I'm calling predictive modeling, where we're just forecasting a sequence of states, whereas on the right, we're predicting like executable trajectories, so either a sequence of states or actions that we're going to roll out into the future. But at the core of it, we're using the same exact generative modeling approach for all of these domains. So one of the main limitations of diffusion models is that they require an iterative sampling process to produce a sample. So how can we address this? So in this next body of work, we use flow models or flow matching models to speed up sampling. And the intuition behind flow models is that we want to learn how to skip sampling steps. So diffusion models rely on stochastic differential equations on the right, while flow matching models rely on an ordinary differential equation formulation on the left. So the score-based models, or the diffusion models, take a meandering path through the denoising process to end up at the final sample. And meanwhile, in flow matching, we similarly want to convert from one distribution to another. However, the denoising path is straighter. And because it's straighter, we don't have to sample as such fine increments and as fine increments as the SE counterpart. Now, both models were essentially predicting how to move a sample from the starting distribution to the ending distribution. And in SDEs, this path is noisy. So the first estimate is not representative of where we will end up. However, in flow models, we want to learn like these straight paths so we can get a better sense of the direction that will lead us to the final sample. So in the figure shown here, P0 represents the starting distribution, and P1 represents the distribution that we end at. So while this figure is showing these distributions in 2D space, our models are dealing with trajectories. So the space of the initial and final distributions are both sequences of state and actions, or state or actions. Here I show the training and sampling for the flow matching models. Crucially, the underlying model is the exact same as the diffusion model, when we're simply changing the training objectives here. We again draw a starting distribution, starting trajectory from noise, and also
I
draw
think we've
a
gotten
trajectory
most of
from
it
our
in little
data.
chats, yeah. Yep.
Then we compute a linear combination of the two, and the goal is to learn the flow field to transform the noisy trajectory into the data sample. Because we're now learning an ODE, we can use any traditional ODE solver to produce the final sample. And here we're using an Euler sampler method to denoise our trajectory. So I'm going to be presenting our results in all three domains now. So beginning with adversarial tracking, we show that our model improves performance. So this is the average displacement error, and across the prediction horizon, the flow matching model outperforms the diffusion model. And additionally, we also ablate the number of sampling steps, so we can show that our flow matching model maintains performance while the diffusion model gets worse and worse as we lower the number of sampling steps. So our model outperforms the diffusion model while simultaneously being fast to sample without dropping performance. Additionally, in the second domain with this aircraft trajectory forecasting work, again, this is a fully observable domain. So we're trying to predict the future trajectories of this aircraft given some past information. And in this work, we show that our flow matching model is able to outperform the previous best transformer-based flight BERT model on both mean absolute error and root mean squared error on the longitude, latitude, and altitude predictions of the aircraft into the future. So this is the current state and then 15 and 30 minutes into the future. And finally, we also evaluate our models on this long horizon planning task. So here we're just using two diffusion or two denoising steps. So we can see in the top here, we're drawing this sample from Gaussian noise, and then we're denoising it down once, and then the diffusion model ends with a collision. Empirically, we can see that the diffusion model has more spread in the center, in the intermediate area time step, whereas the flow matching model, these trajectory points are more clustered, and then we arrive at a sample that actually is successful. On the right, on the y-axis, I'm showing the score. So a higher score just indicates that the models are performing better. And we can see that as we lower the number of sampling steps, our flow matching model still maintains performance, while the diffusion model gradually decreases performance. However, we are seeing that in the higher region, when we do use more sampling steps, the diffusion model is actually better in the large maze. So the flow matching model was better in the medium and small mazes, but the diffusion model is better in the higher sampling step regime. So the takeaways for this work is that we achieve up to 35% increase in prediction accuracy. We reduce the sampling time by up to 100 times, and we also achieve a 142% increase in planning performance. So now we're going to move from these three bodies of work to a real world scenario we're doing for robot control. And here we're tackling an imitation learning problem where the questions we ask are, can we learn diverse skills from user demonstrations? And additionally, can we better guide our trajectories to follow the task constraints? So we evaluate our algorithm in two of these agile domains. In air hockey, the objective is to block the puck from hitting the robot's side of the table. Conversely, in table tennis, the goal is to return the ball to the opponent's side with the desired stroke type. Both domains require swift reactions to plan a motion promptly enough to strike the ball. And the constraint that we would like to enforce is that in air hockey, the end effector should make contact with this puck to block it. And similarly in table tennis, the end effector should hit and return the ball. So we collect a small set of expert kinesthetic demonstrations with 8 distinct behaviors. So we have 4 stroke types: push, lob, slice, and topspin, where we only demonstrate 15 successful demonstrations per stroke. And we also shoot the ball in 2 different angles. So we shoot it to the center, and we also shoot it to the left of the robot. And we compare, so in the prior work, we developed constraint guided sampling methods to incorporate these constraints into the diffusion sampling process. So in this top block, I'm showing both the diffusion model and the constraint guidance that acts on this intermediate trajectory. So here, the gradient is taken with respect to the trajectory after the sampling process, which only causes the local behavior to change. So in the diagram in the bottom left, we show a depiction of the robot arm trajectory, where each point represents like the end effector state at a certain time, and an orange dot could represent represents the puck or the ball that we need to make contact with. So in the original constraint guidance formulation, the gradient is only applied to a single point in the trajectory, which does not cause the entire trajectory to change. Instead, we introduce a sampling method called kinematic constraint gradient guidance, where we make 2 key advances to prior constraint guidance methods. So first, we apply the gradient with respect to the trajectory prior to the denoising step, and this results in a shift in all the points of the generated trajectory to better satisfy the constraint. And second, we apply the constraint to a noiseless approximation of the denoise trajectory tau naught hat. And this provides a more robust gradient that is consistent with the training distribution to better guide the denoising process. So the main takeaway is that we compute the constraint with respect to tau 0, and using this method, we're actually taking the gradient through diffusion model, which actually allows us to update the whole trajectory and enforce our constraint better. So here we show a visualization of how KCGG works in practice with the air hockey example. So we start with a noisy sample here at denoising time step 0. And after each denoising time step, the generated trajectory has some of these points that we're trying to drag to this point. So this is the puck. We're predicting the path of the puck to go this way. And this orange point is the point that we're conditioning on. So we want the generated trajectory to intersect with this point. And we can see that as we denoise our sample, the end effector gets closer and closer to this condition. Here we can compare our constraint method, KCGG, with the previous one. And we show this is in the air hockey domain, so there's just 3 degrees of freedom, so 3 joint angles. The orange one here is the previous constraint guidance method. And the 2 black lines here is where we're applying our constraint. So we can see that as we pull this point towards the puck, it is able to pull just these parts of the trajectory, but is not able to, it produces something out of our training distribution. And then there's this big jump, which is not feasible in the real robot, which means that it is unable to successfully complete the task. Meanwhile, our constraint method in blue on the top here shows that we are able to successfully handle this constraint, and we get a trajectory that actually looks like what we demonstrated. So we compare our method against several imitation learning baselines, so behavior cloning and also ACT, and also the other diffusion model baselines in inherent air hockey. And we found our method to achieve the highest block rate. So the success rate is just how often we block the puck from coming to our side. We also found our method to achieve better improvements in block rates when given the same sampling time budget as other constraint guidance methods. So even though our method requires more time per step, if given the same exact budget, we find that our method in blue at the top here has a higher block rate to the previous constraint guidance methods across all sampling times. Finally, we show that our method improves performance on a real table tennis robot on a variety of strokes, such as push, lob, top spin, slice, and also top spin, improving the performance over all baselines. And here we're defining the success as the robot hitting the ball and returning it to the other side of the table. We additionally have other criteria defining the spin and launch height of the ball for different strokes. So KCGG shows an overall improvement of 17% over all baselines and 125% over prior constraint guidance methods in success rate. So in conclusion, we show that our method is suitable for tasks requiring agile motions with real-time constraints, exhibits diverse behaviors in a single policy, and also better incorporates the task constraints during diffusion sampling, further expanding the boundaries of robot learning for time-critical and high-precision robotic tasks. Okay, so switching gears a little bit, this next part of my thesis will be to leverage these generative models for multi-agent reinforcement learning to increase agent performance. So we're moving back to the prisoner domain, where in our previous work, we built models for tracking and predicting the opponent agent. In this work, however, we aim to learn policies to actively search and track. However, directly learning how to control the assets in this environment is difficult due to the sparse domain. So to make exploration easier, we provide the policy with additional information through a pre-trained filtering module, which is an estimator of where the adversary is at the current time step. So a challenge when learning these policies is that the opponent may react differently as our own policy changes. So for example, let's say we're playing rock, paper, scissors, and when we warm start the filtering module, we're collecting prior data of the opponents in the game. We only observe the opponent playing rock because we're always playing scissors. So now suddenly as our policy starts to improve and get better, the opponent starts to play paper, scissors, and this changes the distribution of the opponent, and as a result, the training process during our reinforcement learning. So we present this prior motion combined filtering module, which takes in has two main branches here. So this one takes in the last detected location and the current time step. The motion model is a simple constant velocity model. And then for the prior network, we're learning where it is based on just the starting location and the current time step. And we weight these two together and pass it to our decoder to predict a mixture of Gaussians again. This mixture of Gaussians is then augmented to the reinforcement learning algorithm such that we can leverage this information during training. So for the results, we evaluate our models on detection rates, closest distance to the target and reward, and we show that our models outperform both non-learning and learning-based approaches. Therefore, we find that our PMC filter can successfully handle the distribution shift during training in our adversarial environments. We also validate our work in the robotarium, where we deploy the policies learned in simulation to real robots. So the ground robots are the search parties, and the detection ranges of the search parties and helicopters are indicated with the blue and red circles. And we can see that the blue agents can successfully track the prisoner with our approach, but not if using the heuristic. Okay, so our prior work has shown that we can accurately predict where the adversary is and track it with a team of agents. However, we have not been able to show that people can use or collaborate with autonomy to improve decision making. So in this last body of work, the hypothesis is that generative LLMs can lower users' workload, increase usability, and produce better plans in the scheduling and motion planning tasks. So in the prior chapters, we viewed the problem as given data of the prisoner, what kind of task would it generate? And an expert might say, I think the adversary is going towards Miami while trying to remain hidden in as many low visibility regions as possible. So rather than viewing this problem as predicting where someone else would go, we could also frame it as given some requirements of the task, what is a route that optimizes these requirements as best as possible? So in this last work, we're therefore viewing the problem in a different lens, where we're doing scheduling and motion planning. And in this body of work, we're going to be testing how language can be used as a modality to specify these requirements. So in the past few years, LLMs have risen to dominance and have been applied to many robotic and planning tasks. Specifically, several works have shown that language models have the capabilities to plan tasks sequentially, with prompting methods able to get better performance out of these models. So recent models such as Cloud and GPT-4 have also shown great abilities for writing code. Here I'm showing 3 separate works: Voyager, LLM Plan, AutoTamp. However, few studies have actually evaluated these models with real users, and they simply measure performance in simulated domains. So in my final body of work, I leverage both planning and code writing abilities of LLMs for scheduling and motion planning. So the domain for this last body of work is Enable Planning 1, where users must control a boat to navigate between certain locations. This domain is fully observable and is used to test both the scheduling and motion planning constraints. And the 4 locations on the map are the cities, the coral reefs, the fishing locations, and the oil rigs. The domain also has weather, where the darker regions of the map here represent poor weather, where the brighter regions of the map represent good weather. So the research question we ask is, can users successfully use natural language to parameterize these trajectories? And additionally, the goal is to minimize the mean span of travel times between locations while subject to various motion constraints. So we designed an underlying scheduler and task planner for this domain. The scheduler takes as inputs the visit requirements and order requirements, and uses a MILP solver to return the order of locations to visit. So the visit requirements may be like the certain locations we want to visit, and the order requirements are, for example, like we want to visit fish A before fish B. Then an ASAR planner is used along with the motion requirements that the user specifies, which basically act as cost functions for the planner. So we built in a scheduler and motion planner as tools for our LLM framework to use. So our natural language user interface is evaluated against 2 alternative baselines. So the first here is this traditional UI that enables users who directly input precedence, visit, and motion requirements. So one limitation of this traditional approach is that which we aim to address with our LLM interface is the need for experts to implement new functionalities to accommodate more sophisticated requirements. In contrast, our LLM method allows users um, to specify requirements naturally using natural language, with the backend automatically generating Python code to encode these specifications. And the LLM has direct access to the scheduler, the motion planner, and all other Python functions. So it enables it to construct novel logic and code to accomplish certain tasks. And the final baseline, or the second baseline, is just a manual control input interface where users directly control the boat's movement by clicking on the map to indicate the desired direction of travel. So we have three different research questions here, which is how does the input modality affect the user's perceived workload and perceived usability? How does the input modality affect the planning time? And also, how does the input modality affect the generated task optimality? And we ran a within subjects user study with 30 participants, where the mean age was 25, and we had 37% female participants and 0% non-binary participants. So the users were tasked to interpret several scenarios through watching a series of videos. So here I show an example of a scenario with the corresponding videos that the users actually watched. So we give users the videos instead of the natural language string, such that they will just like copy and paste the text. Instead, we're testing to see if they can interpret the task based solely on the behavior of the boat. So in this left video, it might be hard to see, but here's the starting location, and it moves to this fishing location here. In the second video, we have the starting location here and moves to this fishing location. And finally, we have the starting location here with this fishing location. And the task of the scenario is go to the nearest fishing location. And so this is one example where the user would have to watch these videos and figure out that that's what the task is. So these videos were created by the same scheduler and motion planner that the UI and L1 have access to. So the user should be able to recreate exactly the task specifications. And each input modality consisted of 5 scenarios, where in each scenario, the users watched the videos describing the task, then recreated the specification in 3 new maps with the given input modality. And for each map, the users had a maximum of 5 tries. So after each input modality, the users took a NASA TLF workload and system usability survey. And as this was with a within subject study, the input modalities and scenarios were counterbalanced. So here I show our LLM agent design, and our interface consists of 2 separate LLM agents. So the code writer and the code summarizer. First, the user tells the code writer what they want to do. So for example, in that last task could have been, go to the nearest fishing location. And the code writer writes Python code and interfaces with the code executor until no bugs occur. So if any bugs occur, the code executor will automatically tell the code writer what the bug was until the code is able to run. Then the code executor has access to both the scheduler and motion planner that we designed earlier. And after running the code, the path is immediately sent to the simulator where the user can see the results. Another LLM agent here on the left, the code summarizer, summarizes what the code writer did for the user. And this is so that if something wrong happens, then the user can ask the code summarizer or can see the summary written here to try and debug the plan. Again, this is an iterative process. So if the user sees something happen that they want to change, they can prompt it again, and it has memory of their previous conversation. So here I show our subjective findings, and on the left we have the system usability score for each of the mode, and on the right we show the workload for each mode. And we find that our LLM-based method significantly lowers the perceived workload and increases system usability. Additionally, for our objective findings, we find that for the total planning time, the LLM is significantly lower than the one used by the user interface. However, the manual control we found also has lower playing time than the user interface and the LLM. So why is this the case? Well, we took a further look and we define, now here we look at path optimality. So we compare the trajectories that the users created with the ones that were created by the ground truth specification. And we found that while the UI and LLM pretty much always have optimal paths because they have access to that scheduler and motion planner, the manual control condition, like users will pause during the game or they'll try and figure out where to go. And that while it reduces total playing time, it reduces the actual path optimality that we get. So our LLM-based method increases playing time efficiency and also maintains the optimality of the paths. So altogether, my thesis explores applying generative models to trajectory prediction and planning. And in this first section of this work, we introduced generative diffusion and flow models for predictive modeling and control, where we introduced novel constraint methods, created multi-agent predictive models, and reduced sampling time required. In the second part of my thesis, we created multi-agent reinforcement learning framework, a multi-agent reinforcement learning framework for search and tracking in sparse domains. And in this last work, we created and validated a natural language interface that improves perceived usability and lowers workload. So some limitations of this work is that the constraint method in the ping pong task is not a hard constraint. So we can't actually deviate from that much from the training distribution. So if we shot the ball in a completely different direction, it won't be able to handle that. In the multi-agent work, we still rely on some prior data to train our filter model, which is a key limitation in this work. And in this last architecture, we try to reduce hallucinations as much as possible, but they may still occur. For broad future work, think exploring multi-agent diffusion for offline reinforcement learning, which is work that we're currently working on actually to handle partial observability and generalizing to novel team compositions. I think it'd be really interesting to integrate the language code generation with the generative trajectory of planning and forecaster from the first part of the thesis, and also combining the diffusion frameworks with reinforcement learning, I think would be really cool. So finally, thank you to all of my collaborators. This is Shen for the multi-agent work, Manisha for the tracking work, Kinman for the ping pong work, and then my other collaborators, Luis, Aaron, Rohan, and Zach. Thank you again to my committee members, and also to my family and friends here, and my advisor, Matthew Doppling. Thank you.
John, are you comfortable leading the Q&A session publicly?
Yeah, what is the order again?
We typically go furthest, geographically furthest to closest.
Okay, I think Andrea is the furthest.
Sounds good. How many minutes do I have? How many questions can I ask?
It's ill-defined, but I'd say 5 minutes is a good rule of thumb. But
Sounds good.
Yeah, we'll have more time during the private session.
Okay. Let's go in reverse chronological order. So from the most recent thing that you talked about to the earlier parts of your talk. So first off, in the fourth part of your talk, can you talk a little bit about some of the maybe good things and also inconsistencies that you've seen about working with large language models and relying on them?
Yeah, so I think there were the good parts were there were a few participants that I ran where I thought that they were going to fail and they said something I would not have said, and it did something completely novel. Like, I didn't expect you to solve this task in this way, but you did it, and the language model was able to interpret it and correct it for you. The negative things are, I think, the ones that everyone kind of had experience with large language models, which are one, the hallucinations, and then two, it does require a bit of prompt tuning for this stuff. So there are like few shot examples in its prompts. Obviously, I did not give it like the exact tasks and scenarios that I need to do here. But the main limitation I think of that last body of work is that because we wanted to run this user study and have it be the same for everybody, the tasks had to be basically like parameterized by the scenario videos. So I would really like to run a follow-up study where instead of showing them the videos, like they create their own tasks, and then we evaluate like how good the model was, the language models were, at satisfying like what the users wanted. So yeah, I think that was like the main limitation of that work.
What do you anticipate to be some challenges or issues if you were to do this thing that you just suggested? So LLMs have pretty good general priors, like general human priors. But if you allow users to specify their own tasks, you might encounter some issues. Can you talk a little bit about that?
Yeah, I think the main ones are I think the cool thing about this work is that the motion costs can be basically anything that's is like an admissible heuristic for our A-star planner. So that's cool because it can do a lot of different things, but also I don't know if the LLM exactly knows what an admissible heuristic is, and it may write like just random Python functions that seem like they want to solve the user, but then may actually fail when we run it with the A-star planner. So I think that would be one of the main limitations of that, of if we just let them like specify anything.
Okay, sounds good. I also had a question about slide 59, I think it was. I think you had this plot where you were showing that the fusion models are better than flow models in high, I don't remember if high sample domains or low sample domains. Like one is better than the other. Yes, there you go. I'm wondering if you've considered, how would you consider maybe a hybrid approach here, where you use one of the models in some cases, the other model in some other cases?
Yeah, I think that is interesting. So yeah, the diffusion models, I think, in more complicated tasks because that stochastic differential equation formulation allows it to, because it's meandering, it allows it to kind of like do this optimization process internally over more steps to get better results. Where the flow matching models, I think, are better in the smaller mazes or like the more simple tasks here. Yeah, I think it would be interesting to do a combination of the both. And I think there are a few models, generative models out there where they're exploring like weighing the stochastic parts of that denoising process. So that noise scheduler, like you can parameterize that differently. So I think people are coming up with like different types of noise schedulers to because if you have like basically like small noise that you converge your SDE formulation to the ODE formulation. So yeah, I think that would be interesting to look at.
Okay, cool. I have more questions, but maybe in the interest of time, it's best if we move on to the next person for now.
Yeah, sure. I think Karen is the next furthest away.
So, um, I I think I'm mostly gonna save my questions for the closed session, unless
Yeah, I think that's fine.
I guess my one simple question is, what are the units on the optimality chart that you
Yes.
showed? Like, is it like a multiplier? Or is it? I read the thesis and I was also confused there.
Yeah, so we just divide like the time it took for them to generate that path with we divide the time of the path that they generated with the path that was produced by the ground truth scheduler and motion planner. So it's a ratio. That's why the 1 is the most optimal, where 1 is saying like we're basically the same, and anything above 1 is saying that you are this many times more suboptimal than the ground truth tracks.
And how are there things below 1, or is that just kind of a weird quirk of the plot?
Yeah, so I think there were some cases where the user like created a path that didn't meet all the specifications. So let's say we wanted to go to fish A, B, and C, and let's say
So
they only
he
went to fish
cheated.
A.
This is a cheat.
Yeah, so then that yeah. So I think yeah, maybe there should be
Okay.
better filtering methods for this plot.
Thank you.
I think Matthew, or should I do the other committee members first? Okay, David.
Let's see, so one question I had was, I think some of these might be for the other section, but on slide 90. I was just curious, is the constraint your agents are avoiding, is that a temporally varying mountain, or is this is that, I guess I'm confused with the plus sign one?
Yeah, so we were using the robot carrying, which has a limited like drawing space for the robots to move in. So what we're actually showing is like the camera is focused on the fugitive, so it's like within the fugitive's frame of reference, and the robots are kind of moving around it. So the ground is moving, but actually like the fugitive is moving. But to test with a real robot, this is what we had to do for yeah.
A follow-up to that one was how in this context, and maybe some of the other dramatic ones, how would you incorporate like temporally varying constraints or probabilistically varying constraints?
Yeah, so the temporally for the temporal ones, that's actually pretty natural to fit in. Let me pull up the slide here. So as long as the constraint is, we can take the gradient through it, so we can say that like, we could even specify for our ping pong robot, like, we want this segment of our joints to look this kind of way, or like, to take a certain path, so we don't have to constrain them to a single point, and we can constrain our trajectories through time as well. The probabilistic constraints may be a bit more difficult, but yeah, we can discuss that. Yeah, after.
And then the other ones I'll say to the other session, but I think another one is on slide 15, just a general question. A lot of this stuff is data driven. What sensitivities, if any, have you done for like how much data is needed for good solutions?
Yeah. So a lot of this work is actually focused on small amounts of data, and we've done a little bit of ablation on increasing that for ping pong. But almost all of the models trained in this slide deck are between like 100 and 150 trajectories for everything. Yeah, I think obviously having more data is usually better. I think in the ping pong domain, when we did do that analysis, there was like a certain number of trajectory we needed before like the performance drastically dropped off in the air hockey domain. So yeah.
How about granularity of like sampling rate wise? Is there like a minimum needed?
In terms of like the sampling rate of the trajectories.
Like you might have
Yeah.
150, but they're only sampled every minute or every 1 second.
Yeah. That's a good question. So I think in general for this body of work, we try to keep the entire trajectory length between at a certain segment. So then the diffusion model could encode most of that like low level and high level features in that sample. So there was like a specific window where based on the domain, we would choose that sampling rate to get like similar window sizes for everything. But yeah, I think it would be good to ablate that and see if it's really like low sampling or high sampling rate, if that would affect the performance.
Sorry.
Okay.
First of all, let me start by saying, really good presentation. This is a really broad body of work. Congratulations on that. So let me maybe ask some high-level questions.
Okay.
So my first question about the first part of the contributions, using diffusion, especially for multi-target tracking.
Mhm.
Can you give me some intuition as to what about the diffusion process and the way in which it's trained is helping you with the data association problem?
Yeah, so I don't think there's, let me pull up this slide.
And quick clarification, I'm assuming the data used to train it had ground truth classes. Right?
Yeah.
You have to have the ground truth facts to train the diffusion process, right?
Yes, so we have the ground truth track, and then I think that implicitly it's like how it's learning that because it's learning to model that distribution of data. So there aren't any tracks with like both of the, like let's say we have 3 agents here, and there's always going to be like 3 separate tracks. So it implicitly learns how to diffuse out those types of trajectories just from the data itself.
Okay, I think this is connected to a larger question I have. So typically, if you use it in a manipulation setting or a robotic setting, like navigation even, there is a certain class of trajectories you're learning, right? Because here the distribution you're learning to denoise is to a particular class. So for something like target tracking, where you could have such a diverse types of motion, have you noticed any issues, especially if you're working with the low data regimes?
Yeah.
How diverse does that data set have to be? Like, for example, if you test it on a trajectory that's a periodic orbit, what do you think the diffusion process would do?
Yeah, I think that's definitely a key limitation. So in this body of work, we basically assume that the training to test distribution is the same. So we didn't really test on like all of these different weird things. Like, okay, let's say this agent will just stand in the corner for 10 hours.
Yeah.
I don't think the diffusion model will be able to learn that. So I think there are probably more things that we can do to figure out like if there are more general strategies that we can put into the diffusion modeling framework so that it can learn some of these things by itself, or yeah, right now it's just kind of like a completely data-driven approach. So we don't have those like expert strategies that it can learn from.
Okay, fair enough. My next question is about the constraints.
Okay.
Do you ever have more than one constraint?
So in the diffusion for the target tracking, we had like mounting constraints, and also there were constraints where if we like detected where the agent was, we can put it in the maintain kind of constraint, where you can formulate it that way. I've tried. I think the most I've gone up to is like 3 constraints where you can back target through all of those. But for the ping pong pass, that was just a single constraint that we were using. So I haven't explored like how many different constraints we can keep adding on.
That's fair. If they happen to conflict, how would you go about solving it?
It's a good question. So,
Or what do you think would happen? Let's say you don't change anything.
yeah.
What do you think would happen? Would that be a mode collapse?
Yeah, I do think in the first version of this, the one for the trajectory modeling, I think it would collapse, and it would probably the gradients would push against each other. So you would get a trajectory that probably doesn't look like anything and might have like these big dysregularities. In the second body work where we're doing the gradient through the diffusion model, maybe one of those constraints might be met, the other one may not be met, but it will still at least look like something within the training distribution. But I do think that one of those constraints, yeah, won't be met in that body.
That's the intuition I was looking for.
Yeah.
Thanks. The next question I have is, I want some clarity on the second contribution, the class of contributions you talked about. So that one is the multi-agent reinforcement learning one.
Yeah.
Am I right to think about this as the contribution is to develop essentially this estimation or filtering technique, and then you just stack it onto an existing model algorithm? How should I conceptualize this contribution?
Yeah, I think the main contribution here is to add some of this expert knowledge into this filtering module. So rather than just doing like complete end to end with only like fully connected layers for the filtering module, it's like specifically building this model for the reinforcement learning task. So breaking it up into these separate components we show that it's better for this task. So that's how the way we're thinking about it.
So it's sort of agnostic to the particular model. Like, for example, it wouldn't matter
Yes.
whether you're doing parameter sharing or you're doing policy gradients or
Yes.
based. Okay.
Yeah.
Okay. So my final thing is not really a question, it's a potential pushback, and I want to see what you're saying to defend it.
Okay.
So this is particularly about when you're doing the user study, you're
Mhm.
showing the differences between the interface versus LLM. And one of the claims you made is that people found the traditional UI to be very cumbersome to use. And if actually go back a couple of slides where you introduced the three. Yeah, you have 3 screenshots, not the research questions. One is, right here. What if people found this to be cumbersome to use because you are also asking them to label in addition to just specify?
Yeah, so that's a good question. So
And so let me also add something for context. Obviously, your claim would be fine if you're just providing an initial prompt, but you suggested that it's a feedback loop. So I'm hypothesizing a scenario where if I have an interface like this, all I have to do is specify and I'm done. Here I have to specify an initial prompt, see what the agent does, and then be annoyed with it and fix it.
yeah.
So I'm trying to simulate that user experience.
Yeah, so the way, actually let me pull up the way we design our 5 scenarios is that sometimes you would have to re-specify that in the UI, whereas ideally in the large language model, you would not have to. So we have these 3 scenarios where you could basically specify everything in that UI, and then you can press run, and then just keep pressing start, and then it would be fine. But we specifically wanted to test our LLM to see if it could like surpass the UI by writing the Python code at the back end. So then if the user specifies that correctly, or the LLM plus user specifies that correctly, then they can just keep repeating that generated like requirements over and over again. So in some ways, I guess you could say that like we design our scenarios to get that, like to see that result, but yeah.
But so that's where you really claim the potential advantage. So
Yeah.
Okay, that's fair. Thank you. That's it for me.
Thanks.
Hi, Sean, I have a question for you. Can you talk to me more about your final component of your dissertation and how you think your work can help solve problems related to hallucinations with large language models in planning contexts, and what you really think is needed for future symbolic planning systems that can be integrated with LLMs?
Yeah, so I think for this last so the question for those online was how can we address hallucinations, or how does this body of work help address hallucinations for LLM? So I think for this body of work, it's like the first start to how I'm thinking about addressing hallucinations, where we have like an execution module and also a summarizer module, but they should be like grounded with each other. So like the code summarizer, if it's correct, like should evaluate the code writer and vice versa. So I think in this architecture, like it'd be interesting to eventually fine tune these models or something such that they kind of fight with each other, and like not fight with each other, but similar to how they're the models in like Gale or GAN work, where one is like the generator, where we have a code writer, which is the generator, we have a code summarizer, which is the discriminator. I think that kind of architecture where they're kind of talking to each other and trying to figure out like how correct the other one is may lead to a reduction in hallucinations further down the line. But yeah, I think for this work itself, the way we're addressing hallucinations right now is basically to like the code writer and the code executor are very tightly coupled. So the small code errors that occur there will get solved. And then the human will have to kind of like deal with the other small percentage of the hallucinations that occur elsewhere.
Great, thank you very much, Sean. Any questions from the general audience?
So
Does this work? This is how I talk, then people can hear me, or where's, is it fine? Can you repeat my question?
yeah, I'll
Okay, thank you. So you, in your, I think your first work, it was with the boat, or the work with the boat, where people have to like send the ship to different locations. You also include weather. I'm wondering, is that changing weather? And so how could your model, for example, how could you validate your model with external disturbances like weather basically is? Could you clarify or talk about that a little bit more?
yeah, so you're talking about this body of work, the natural language one, or the
one with the ship, so
yeah.
I guess.
Yeah, this.
Yeah, the previous one,
Yes, sir.
yeah, this.
Yeah, so currently the weather is static. And for temporally changing weather, I think that's actually the way we have it set up in this framework is to like that's a question for the underlying method. So right now we're just using like A star. So there are temporal A star methods or other like pathfinding methods to account for that. But yeah, in this work, that wasn't the focus of the work. So I would say I think we could handle temporal weather as long as the underlying tool there is good enough and it has a good enough interface with the language model to handle with.
And so in general, like how would you treat like external disturbances or anything like, to make sure that your solution still works?
So by external disturbances, do you mean like let's say there's like another agent that suddenly comes in the environment or something like that, or yeah, so I think right now it's set up where we're kind of like one-shotting these paths where it's not reactive. I think it would be interesting to combine this with like maybe the underlying model is like a reinforcement learning agent and it can react to some things, and maybe you can specify that. Otherwise, like if we're doing like the other bodies of work that people have been doing in robotics, where they just take a language model and then like, or not, they're training their own like multimodal language trajectory planning action model, where you just have one transformer that's kind of do everything. You have a big set of data set. That could be interesting if you have like the data and manpower to do this, where then it should be able to react like more to those external disturbances because it's taking in like states and actions at a high frequency instead of just doing like planning from the top down and then executing after that.
Awesome, thank you.
Really related, is this a snapshot of actual weather that you took that snapshot from, or is it just some noise that you added?
Yes, it's some noise that we added. Yeah.
Can you go to 34?
Yeah.
So you say the architecture is invariant to the number of agents, that's with the cross attention.
Yeah.
The cross attention though, is it aware of the number of other agents, i.e. if I'm agent A and I assign agent B to go do a task, what's to say that I don't accidentally reassign that task to agent 1500 as this scales?
Yeah, so that's a good question. So in this domain, we're only training and testing on like the 3 agents. So it is invariant to the number of agents, but in terms of like how it's should specify, let's say specify a task to the other agents, in this framework, like we would hope that it would learn that from the data distribution that multiple tasks are not assigned to the same other agent. And if the model has done it correctly, then it shouldn't, with the cross attention mechanism, like it should communicate that implicitly to the other agents, and not produce that in the data distribution, in the testing data. I think, yeah, this is part, I do think this would be a future work where, like how well does it extrapolate or interpolate, when you go from like 3 agents to 5 agents, let's say you only train on 3 to 5 agents, will it still work with 7 agents, like, I'm not sure, but yeah, I think it'd be cool to explore. Okay.
Thank you very much, Sean.
Please grab food, and thank you to Misha and Kinman for grabbing it.
Sure that you respectfully take out the little radio out of your.